Welcome, everyone. Pleasure to be back here in the flesh. So I want to continue on this theme of random matrix theory and its natural sciences, less so in number theory, more to do with quantum chaos, which is what John Keating was alluding to. Let's say. As we saw, the global impact of the connection between the Riemann zeta function and random matrix theory, and we heard a lot about its impact in going from random matrix theory to the zeta function. But I want to discuss manifestations in the field of quantum chaos, or more precisely, the spectral theory of Laplace. And in that theory, as John was describing, the Riemann zeros serve as a toy model, which means that it's something that's much easier than the problem we want to attack. So that, as we heard yesterday, but the real thing is something that I want to discuss today. And to keep the discussion focused, I'll only look at one statistic, which is the number variance. And explain how it helps you pick out different universality classes and see how it works for the eigenvalues of the Laplacian on the Riemann series. Okay, so what is this number variance? So you have a, let's say, matrix. That's a unitary matrix. And that gives you a sequence of eigenvalues. And you look inside the spectrum, pick a window, which is supposed to contain L eigenvalues. When I say supposed to contain, means on average in a suitable sense, which I'm leaving vague on purpose. Then take the window position to be a random variable and ask for the statistics of the number of zeros which lie in such a random window. And in particular, one statistic, the first non-trivial statistic, is the number variance, which means you look at the deviation of the actual number of eigenvalues in this window from the expected value. Okay. This is called the number variance. You look at the average over positions of the window, or alternatively, you can take the spectrum itself as being random, meaning you take a random matrix and then you average over matrices. Or you could do both. So this is the number variance, just the variance of the number of eigenvalues in a window. So what does it look like in random matrix theory? So we take an n by n matrix and look at a window which is supposed to contain L eigenvalues, and we think that L is growing with n, but still smaller, significantly smaller than n. So if we take a matrix to be diagonal, meaning you just take n random numbers, then, as we know well, the fluctuations are going to be of size square root of the total number of the expected value. So the variance will look like L, like the expected value. That's the Poisson model. On the other hand, if you take either GOE or GUE or COE or CUE, then the number variance is much, much smaller. It grows logarithmically with the number of the expected number of eigenvalues that you're looking at. This is something that I think was known to Dyson, by Dyson. It was known, I don't remember if it was saying someone else. In any case, for GOE, the number variance is asymptotically 2 over pi squared times log of the expected number of eigenvalues. And for GUE, it's half of that. So this is called rigidity in the literature, meaning there's the very few very small fluctuations from the total number of eigenvalues. While for the Poisson case, the fluctuations are very large. And this statistic distinguishes GOE from GOE. For COE and COE, it's the same number. Same number. Okay, so let's go to the toy model, to the Riemann zeros, and as several people said, Feldberg studied this quantity, matrix, and he showed that in our language, the number variance of the Riemann zeros is that of GUE. He didn't say GUE, but he computed what it was, and it's 1 on pi squared times log L, which is the GUE answer. Then once you know the variance, you can discuss the distribution of a normalized variable, and we discuss the central limit theorem. So just this one statistic. Okay, and here is the paper that John Keating mentioned on the first day, when Michael Berry worked out a theory for the corrections from the main term. And here's a use of Andrew Odlyzko's data and to plot the number variance of the actual Riemann zeros. These are the dots. Then the dashed curve here is GUE, and this curve is GOE, which is clearly wrong. GOE looks good, at least initially, and it is good because 40 years earlier, Selbert proved that it was good up to a certain range. So this theorem is unconditional, by the way. It's quite easy to do it. It's a Riemann hypothesis, but Selbert did it unconditional. So as I was saying, for me, the Riemann zeros are just a toy model. I want to use them to use the intuition from them to study more complicated systems. And these are the eigenvalues of the Laplacian. So instead of the Riemann zero, we look at eigenvalues of Laplacian on a surface, just to make things simple. So you start with a surface, compact, smooth-oriented surface, and you put a Riemannian metric on it. And that gives you a Laplace-Beltrami operator, which has eigenvalues. So you're trying to find these eigenvalues, and there are lots of them. There is, in fact, an orthonormal basis which consists of eigenfunctions of Laplacian, so there are lots of eigenvalues, and the spectrum is just a sequence of discrete numbers. Eigenvalues don't have any accumulation points, and you can count how many there are. And Weil's law says that the number of eigenvalues up to E scales linearly with E. This is special to surfaces. The prefactor, which is the area over 4 pi. So this is units from a natural system, and you can see the spectral staircase where you jump by 1 whenever you hit an eigenvalue. There's a multiple eigenvalue, you jump by 2, and you see clearly that it grows linearly. And this blue line is that term. So we can play this game of number variance on such a sequence. So you take a random window, which you think will have L eigenvalues, and the side of the window is going to scale to be a multiple of L using Weil's law, and you ask what is the variance. And then the, let's call it a conjecture that Michael Berry formulated, was that if the window is not too small but not too large, then there's a universal behavior which depends only on the dynamics of the geodesic flow on the surface. So in particular, if you take something like a flat torus, then the expectation is that the number variance is Poissonian. And if you take a chaotic surface, which means the geodesic flow is chaotic in a suitable sense, then you are supposed to get random matrix theory behavior. In particular, for this particular problem, you will get the number variance behaves like 2 over pi squared log L. Again, L is the expected number of eigenvalues in that window. So examples of, so these are two extreme cases. Most surfaces are sort of in the middle, but this special case when the dynamics is very regular, and examples of the round sphere, where every geodesic is closed, they're all equators, is really an extreme case, or the flat torus, or surfaces of revolution. So in that case, the eigenvalues can be related to lattice point problems. We'll see this in a second. And the other extreme is when the geodesic flow is chaotic, for instance, it's ergodic, and there's hyperbolicity, the nearby it is diverge exponentially. And the example that I want to discuss is hyperbolic. That's only discuss here. In any case, I will show you a few examples where this is known in the integrable case. In the hyperbolic, in the chaotic case, there are no theorems, which is why it's a good subject to work on. So let's do the integrable case. In particular, the standard flat torus. So what does it mean? You take a square, identify opposite sides. You just use the flat metric. So the Laplacian is just the standard Laplacian. You apply it to functions which are periodic in both variables. So product of sines and cosines. And then it's easy to find eigenfunctions. They're just cosines and sines. And the eigenvalues turn out to be sums of two squares. So now we can forget about all this nonsense and just take this arithmetic problem of statistics of sums of two squares with multiplicity. So in other words, if we want to prove Weil's law here, this is the way you prove, the first way you prove Weil's law, like doing this example. Weil's law is just you count the number of eigenvalues up to E, which means you count lattice points in a circle. That is the area of the circle. So that's Weil's law in this case. An interesting problem that is very old is to understand the size of the remainder term in Weil's law. In this special case, it's called the circle problem. It has an old history, and Hardy's careful conjecture was that the remainder term is e to a quarter plus that's the law. Now I'm trying to understand this. The truth here, you compute the variance. This was done by Kramer, who I think Pierre Louis knows from risk theory. And the answer is consistent with Hardy's conjecture. So if the difference, if the error term is e to a quarter, then squared it's e to the half, and average it's still e to the half. So if there's an exponent, it will be and it tells you that the remainder term can't be smaller. So this is an energy average for a particular flat torus, but it works the same way for all of them. You can also, as I said, try to average over an ensemble. So here, average over all flat tori. I'll show you how to do this in a few slides. But the result was done relatively recently, and at least we know an upper bound for the total variance, which is again consistent with this Hardy conjecture. Now, if you look at small windows, which is what is interesting for me in this universal range, then this was studied by Pavel Blecher and Joe Leibovitz in the 1990s, and Freeman Dyson was involved, and Jean Bourgain. For instance, one of the results is that if you take instead of a square, a rectangle, which is Diophantian in the sense you either know or don't want to describe, then you get something that's consistent with this conjecture. It's consistent with the Poisson model after you ignore the symmetries. Okay, so this is the integrable case. This we should think of as the easy thing. I'm not saying it's easy because, for instance, the circle problem is still a problem. It's relatively easy because we can parameterize the eigenvalues in terms of lattice. Now let's move to the chaotic setting. And for me, the first thing is instead of flat surfaces, which means constant curvature 0, you take constant curvature but negative. So any surface of genus at least two holes, will admit metrics of constant negative curvature. This is the information theory. They are called hyperbolic metrics. And any such hyperbolic surface can be uniformized the same way we uniformize the flat torus by Euclidean plane modulo lattice. You uniformize it as the quotient of hyperbolic plane modulo a lattice, and meaning a discrete subgroup of integration preserving motions. So either the upper half plane model, unit disk model, it's easier to draw pictures here. And that for us is a hyperbolic surface, so just the quotient of upper half plane by a lattice. And it is a fact that the geodesic flow for such a negatively curved surface is chaotic, so particular ergodic and so on. And the Laplacian, the upper half plane model, is just the standard Laplacian with factor. And we want to find eigenvalues. We mean look for eigenfunctions of this on a fundamental domain with suitable periodic boundary conditions. So the Laplacian is simple, but boundary conditions are what makes this complicated. Now, nobody knows a formula for the eigenvalues here. For all, but we still have Weil's law, and Weil's law says that the number of eigenvalues grows linearly with the energy, and the prefactor is the area over 4 pi, which is just the genus minus 1 by Gaston. Okay, so let's play this game of computing number variance. And you can either do an energy average, which I don't know how to do, or as was done earlier, do an ensemble average. So you take several hyperbolic surfaces of genus 2, you compute a stretch of eigenvalues, and then look at the statistics of this random set of eigenvalues. So this, I'm looking at the study that was done by Alwish and Van Steiner over 30 years ago. So they took 30 different genus 2 surfaces. Now, genus 2 are hyperelliptic, so that's the involution. So the spectrum breaks up into odd even classes. So you get actually 60 different matrices, each of size 75. This is what they did. I'm just explaining what they did. And then you compute the variance of that sequence, number variance of that sequence. And here is the plot of the data. The data is this solid line. It clearly is not growing linearly with the number of eigenvalues. And GOE doesn't seem like a good thing. GOE seems fairly good, at least initially. So one of the reasons they did this was that they complained that it's very difficult to actually generate lots of eigenvalues with good precision for an individual surface. They were using a finite element method. Wouldn't trust this. So they just collected a lot of eigenvalues by doing it in many different surfaces. Okay, and the results support that you have GOE. I think it's very hard to argue with the results. So the conjecture is that every hyperbolic surface will have GOE statistics. But this is a little imprecise because it was discovered around the same time that there are surfaces for which GOE is. And there was some confusion about what is the situation, but as it turns out, the differences were arithmetic. So there are arithmetic surfaces. For instance, if you take the lattice of the SO2Z, never mind. In fact, this is clearly arithmetic. And in that case, the statistics are not GOE. Already Selberg knew this, but he wasn't using this language. Certainly this wasn't understood in the physics community. Selberg did the analog of Kramer's computation, but for things that look like SO2Z, for certain unit groups of quaternion algebras, it's precise. And what he showed was that the number variance is big. It's not growing logarithmically, it's growing polynomially. So this is the analog of Kramer's result. Wenjilu and Petersson actually did the computation for its universal, which is what I'm interested in. And more remarkably, they actually looked at, they understood what means all arithmetic surfaces, and it's a much more difficult thing. And they showed that for all arithmetic surfaces, I'll define arithmetic surfaces in a second, the number variance is again very, very large. So instead of growing logarithmically, it really wants to grow linearly. But nobody, to my understanding, knows how to prove an upper bound on the number variance, but to show that it's not GOE, all you need is a lower bound. So the lower bound is almost what you get in plus. Again, this is not for all windows, but it's within the universal regime. So here are the results of numerics by Charles and Charles Schmidt. Initially, they were taking these non-arithmetic, let's say, surfaces, and you see GOE, and then shockingly, they took unknowingly took an arithmetic triangle and saw linear growth. So this is the linear growth we understand in these examples. I do not know whether there are surfaces which are non-arithmetic where you will see this. I'm just telling you what I know. So arithmetic surfaces have large number variance. Others, we don't know. Is this a criterion for arithmeticity? I don't know.
Conjecture about whether it's Poissonian? Conjecture to be Poisson?
It is conjectured to be Poisson. Numerically, it does look like Poisson. But again, this is not known. Okay, so I want to study this. Just make sure I haven't skipped anything. Yeah. Will I give a definition of arithmetic surface? No. It's not important for the rest of the discussion. Okay, so I want to play this game. I actually want to analytically do this experiment that Aviv and Stein did. I want to average over all surfaces. Now, to do harmonic analysis using sharp counting function is a nuisance, so I will use a smooth counting function. And so you just count eigenvalues in a window, but with a analytic way. Already Dyson and Meta, in this series of papers that was mentioned 2 days ago, they computed the number variance of this, the variance of this, it's called the linear statistic. I'll keep calling it number variance. Computed the variance, and not only does it not grow linearly as it would in the case of Poisson. So for Poisson sequence, the variance of this linear statistic still goes linearly with vector number of eigenvalues. That's an easy computation. But for the GOE and GOE, not only does it grow slowly, it actually saturates to a constant value. And the difference between GOE and GOE is this factor of 2. So it's a simple answer depending on your test function, but there's a factor of 2 for GOE and a factor for 1 for GOE, which is the Riemann zeta case. And we saw this earlier when we looked at the actual number variance. We had log of the number of eigenvalues times either 2 over pi squared or 1 over pi squared. So that factor of 2 remains there. Okay, and the goal is to compute the variance of this linear statistic as I average over all surfaces of genus 2. And I want this to be twice this answer. That's what I want. I don't want this because that violates all the numerics.
All right, what surface are we counting eigenvalues on?
Right now, give me a surface. I will compute this linear statistic. Your number. But I want to average over all surfaces of genus 2.
Okay.
That's what I want to do.
Okay, but how are you, I don't know. Okay. How are you picking these surfaces, or like? But how are you picking these surfaces? How do you get there? Okay, good.
Depending what I want to.
Okay.
Okay, let's answer the question. The set of all hyperbolic surfaces of a given genus actually is essentially a manifold. Dimension 6G minus 6. So the genus is a case 2, otherwise you don't have hyperbolic surfaces. So this is the positive dimension. So it turns out this set of all surfaces has a natural manifold, orbital structure, and we call it a manifold of essentially a set in Euclidean space. So this is 6G minus 6 independent moduli. That's the end. And this is the subject of Teichmüller theory, so I'll just tell you the facts right now. So it's this space of all surfaces is actually the quotient of a Euclidean space of dimension 6G minus 6 by a discrete group called the mapping class group. It's a non-compact space, and it's equipped with a natural probability measure, which is just the Euclidean measure on this Hilliard space, Teichmüller space, and that measure is invariant under the mapping class group, and so it descends to a measure, a finite measure on the moduli space of all surfaces of genus G. And Once you normalize it, you get a probability measure, and then you can discuss random surfaces, and you know how to average over surfaces. So that is the answer to your question. So you still have to do it. So let me, I will have time to actually describe this. Let me show you how it works for genus 1. Genus 1 is not hyperbolic, right? Nonetheless, there's a nice moduli space, which I think most people will know. So here is how it works. So first of all, so genus 1 means torus. A torus. And we put a flat metric on the torus, and we want to look at the space of all tori, flat tori. Now, any flat torus, as I said, is a lattice, is a quotient of the Euclidean plane by a lattice. So we first construct a discovering space, Teichmüller space, by a genus setting, which is the set of all pairs of flat torus with a marking. And the marking means you just take a basis of the, in this case, of the homotopy group, meaning a basis of the lattice that uniformizes flat torus. So you count each flat torus many, many times, because there are many bases. So how to describe this Teichmüller space? Well, I just have, it's just a space of, you have to give me a basis. So since I have freedom of scaling, which I don't imagine in this case, and isometry, I take the first vector, so just a standard unit vector. And the second vector of the lattice, the second base element of the basis, is any vector which is linearly independent of the first. After reflection, you can make it just any element of the upper half space. So the answer is that the Teichmüller space here is just the upper half. Now, what matters is the lattice, not the basis. So a lattice has many bases, and the freedom to do so is GL2Z or SL2Z once you put the extra structure. So the result is that the moduli space is just the quotient of upper half space by SL2Z, which is something we all know and love. Here is what it looks like. It's a non-compact space. It's an orbifold. There are two corners here and here. And there's a measure on the upper half plane, just the hyperbolic measure, which is invariant of the SL2Z. So it descends to give you a finite measure, as it turns out, on this moduli space. And that's how you choose a random flat torus. So if I want to average over flat tori, I just average over the fundamental domain for this. So this is something we all know how to do. The higher genus case, time, I don't know how to operate this apple. Okay, so I had time to discuss Teichmüller space in general. So instead of the upper half plane, I'll explain what is this Euclidean space. So you look at all, so you fix a surface and you look at all hyperbolic structures on it. So that means you look at an a diffeomorphism for your fixed surface to the hyperbolic surface. And there's two such markings called the marking equivalent if they differ by an isotopy. Then it turns out that the set of these marked surfaces, I will show you in a minute, is naturally parameterized by 6G minus 6 real variables. And so it's just a Euclidean space of dimension 6G minus 6. So here's an example of a marking which I stole from a wonderful book by Benson Farber and Dan Marguerite. So you take your fixed surface and look at different markings. So you get the same surface isometric, but the basis is different. This is what we did for flat Torah. So the moduli space is, you forget about the marking, as we did in the case of flat tori. And it turns out that this forgetting is done by moving by a group called the mapping class group, which is the analog of SL2Z. It's just the group of connected components of the diffeomorphisms of the surface. Now I want to describe the measure, the analog of the hyperbolic measure. This is called Weil-Petersson measure, and the useful way to think about it is to use the fact that any hyperbolic surface can be broken up as a union of what are called hyperbolic pairs of paths. So here's an example of how to take a genus 2 surface and break it up as a union, how to get it by gluing two. So here are two pairs of paths. This is a pair of paths, right? There's 3 boundary components in genus 0. And then what you do is you glue them together here, the blue ones. You glue the green ones here, the red ones here, and you get the surface. So any surface has a pair of fancy compositions. There are actually many compositions. Now, so what are the parameters we have here? We have the length of these boundary components, 3 boundary components. So that's 3 diameters. And there's a freedom when you glue them, you can twist and then glue. That twist you can twist by 17 times 2 pi or by pi over 4 or something. That's the twist parameter. That gives you another 3 real parameters. And it is a fact that this is all you need to describe purposes. So every surface has a decomposition like this, gives you this parameterization. And then the measure that we use is just the Euclidean measure in these parameters, the length. Now, it is a fact that this measure is independent of which decomposition pair of fences I use, and that the measure is invariant under the mapping class. So this is a theorem of Weil-Petersson 40 years ago. It's called Weil-Petersson magic form. Now it's that mouse is just a old-fashioned thing. Good. All right, so now I am allowed to state the results. So I take this linear statistics and compute the variance. And the answer is that when you average over surfaces, I have now discussed how to average over surfaces. You get, okay, the short answer, which is what I would like to conclude. So my time ran out, is that you get geo. Okay, now the small parts. Small parts. I'm actually lying. I can't do this. So I'm hoping most of the audience is colorblind. Red. What I'm saying is true only in the limit of large genes. That is. What I can prove is only what happens.
What's L there? Fixed?
What is?
How big is L?
So there are 2 limits here. Okay, so let's forget this large gene. The universal regime is when you look at windows whose length is less than the square root of the energy. That's the regime here. Okay, so you take a limit of large energy while with windows which are like e to the 1/4 or something. And that's supposed to give you G.
That it can be arbitrarily small L. L, can I fix L?
No. It has to go to infinity. Yeah, it's less than means the length of the window is visible to E, but it's going to infinity. So without this red thing, this would be exactly what is the statement. Let's say for if you average over all genus two surfaces, you get geostatistics. That is what you want.
But that's just for the smoothed out version. That's F.
I only know how to do it for the smooth version. I think it's true also for the sharp counting. This is a problem of harmonic analysis. I'm happy with this because it is, as people in that building would say, it's a diagnostic of which random matrix ensemble you have. It picks out the 2 and the 1 for GOE and GOE. It also picks out Poisson quite easily. So for me, it's as good as the counting. Okay, so the caveat here is that before taking large energy, I have to take large things. I believe the result is true without this. I don't know how to do it. This is crucial in the proof that you can believe.
Possible to quantify the limit in G, like give an error.
This has yeah. This counts with remainder terms. So there's like a 1 on G or 1 over roots G deviation, and then here you can also quantify. Everything is quantified. It's not there. It's harmonic analysis. Okay, so this is the result. So this is the first, the only time there's any rigorous way of getting GOE statistics in anything.
Is there hope of getting higher order statistics?
Yeah, I believe it should be possible to compute all moments. And we know that both in random matrix theory and in Poisson, once you normalize, you will get a central limit theorem. So this should be doable here. I haven't done it, but it should be doable.
Just to clarify how big L is. Can L be, it has to grow a little faster than e to the half minus delta or something? Is that what you're saying?
No. Ideally, not ideally.
I mean, can you get down to the eigenvalue spacing?
No. It has to go to, so the number of eigenvalues in the window has to grow. Otherwise, it's a different regime, and you see it in the mechanics. This is the difference in Selberg's theorem. Let's think of Selberg's theorem when he computed the number of variants for the Riemann zeros. He could take windows, any window which contains lots of eigenvalues, bigger than 1 over log, but he can't do 1 over log.
No, you can't get that. Yeah, but I'm just asking, that's why I'm trying to understand how big L it can be. And this formula is very similar to what Katz and I did. It has a G limit and then the L limit, but there we were able to, we had very strong angular distribution. So I guess we'll see in a minute what you do.
Okay, so what's the secret? So this is something that I like to do, but the technology to do that only became available due to the work of mine, Mizrakhani. And then there was a lag. There's a paper of Freeman Dyson called called Missed Opportunities. So the technology to do something like this was available in Mirzakhani's thesis, but suddenly I didn't think it would happen. There's a paper of hers that was published only 3 years ago, which really is very useful for this, and she uses it. This was published posthumously. She passed away sadly in 2017. It was completed collaborative Weil-Petersson. So they use her theory to compute averages of various things, geometric things over moduli space. Just here's a nice example. So you take a surface of genus 2 and count how many closed geodesics there are of length less than 10. So that gives you a statistic, right? For each surface, you get this number. It's a random variable on this moduli space of surfaces. And you can ask what is the distribution of this random variable, the number of closed geodesics of length at most 10. And she and Brown-Petrie prove that this random variable has a Poisson distribution in the large genus limit. Parameters, there's a parameter which depends on the cutoff on the 10. So this is the kind of result that the theory is capable of producing.
That result is about all closed geodesics and not just simple ones.
Yes. It's too simple in a second. That's a very important point. So, for instance, we know that in the theory of primes, there is a theorem without a proof of that form. Right? The primes have a Poisson distribution on the suitable scales, on the scale of the mean spacing. It's a fact, it's not. So this is the analog. And here's my lecturing about this. To go back to Akshay's moment. So what is this theory giving you? So it allows you to compute averages of certain functions, certain random variables on the moduli space. The random variables called geometric functions. So what you do is essentially you count the number of simple closed geodesics on the surface. That is something you can do. What is simple? This is non-simple. This is a self-intersection. So a geometric function is a function which is a sum of length. So you take the surface and you count all simple closed geodesics of a given topological type. And given topological type is equivalent to saying that they are in the same orbit of the mapping class group. And for instance, in the genus 2 surface, there are two types of simple geodesics. There are separating geodesics and non-separating. Separating that if you cut the long geodesic, it breaks up into two connected components. Non-separating is when it doesn't break. And so that for genus 2, there are two types, I guess. For genus 3, there's non-separating and then two kinds of. So, no, genus 4, actually. Okay, so she can compute averages, expected values of such random variables on the moduli space, and the result is it's a beautiful and amazingly simple formula that in the large genus limit. In the large genus limit, the expected value is a simple thing. A very, very simple thing. There's an explicit formula for it. Again, this very special kind of function. Good. And that's the ingredient that ingredient that one needs to do this average. Okay, so what's the scheme? What's the program? How do you compute averages or variances of this linear statistic? We don't know how to handle eigenvalues. So you use the Seldon trace formula to convert this linear statistic to a sum over all closed geodesics. It's actually we're saying all closed geodesics, not simple geodesics, all of them. Then, to compute the variance, we need to compute the second moment of this. And then you get a lot of pairs, and you get pairs of closed geodesics, and there are many kinds of them. And you have to pick out which give you the main term, and which are presumably garbage. It turns out that the main term is given by two types of pairs. One are the diagonal terms, meaning just take the same geodesic twice. One is, and they have to be simple. And the other is pairs of simple disjoint geodesics, so that the union doesn't separate the sets. And I use this integration formula that I described before to get the asymptotics of these terms, and then the others, most of the others are not of this kind. Most of the others are not of this kind. The others you have to show are negligible, and that's a separate consideration that you have to do. Now, just as an aside, if we're counting closed geodesics, then there's an exponential number of closed geodesics of length up to L. This is called the prime geodesics theorem. The number of closed geodesics of length up to L is growing like e to the L over L. On the other hand, the number of simple closed geodesics of length up to L grows polynomial. This is another, okay, that was known, but Mirzakhani actually computed that in thought. So there are much fewer closed geodesics, simple geodesics than all closed geodesics. Nonetheless, they give you the main contribution. Anyway, so you got to do all this stuff, and this is not the place to do this, but at the end of the day, you get this GOE variance. Okay, so what we did today is I showed you how to use this linear statistics to pick out various random matrix ensembles as they occur in spectral theory. So flat line, you get Poisson statistics for the Riemann zeta function, which presumably is not a spectral problem. You get GOE statistics. This was known in the 1940s. And for hyperbolic surfaces, you get GOE statistics, at least in this large piece. All right, thank you.
Questions, further questions?
That's a question. So, as I'm sure you know, if you try use this to understand that the random hyperbolic surface, up in the spectrum, but you were sort of playing somewhere in between. But for eigenvalue of quarter, because of these simple closed geodesics and the next term, people are stuck at 3/16. On the other hand, if you look at the random SN cover as higher than magnitude, you are able to get up to a quarter, which is greater. So my question is, have you tried to use, instead of the random Weil-Petersson metric, averaging,
To use the other
the SN cover, which seems combinatorially much friendlier, and then you get very close to the graph case. And in the graph case, all these things are much easier to understand. Well, not easier.
No. So I dispute the. I thought graph theory 20 years ago. I thought graph theory was simple. I learned to regret this. So here we're saying that other models of random surfaces. For instance, there is a model that the late Bob Brooks and Ryan Markover constructed. The random Belly surface is constructed out of cubic graphs, and there's a random color model that was studied by Doron Puder and there's no a priori reason that they give the same answer, except that you are supposed to compute. I only did the computation here. I don't know, I haven't tried seriously to do a computation in one of these other random models.
That gets over this very serious hump so far.
Right.
Because you need a free group, they use some non-trivial stuff.
Right. For
representation.
me, this is a more natural model, but again, I think I've been trying to convince my colleagues who want to do this, to do the same computation for these other random models.
And so, as you know, in the graph case, if you take a random graph, HTR and all these co-workers are extremely close to proving.
They're very close to proving GOE for random regular graphs, but they still need, someone describes it, they still need the degree. So initially I was interested in degree 3 random graphs, and they can't do that. They need a degree to grow. But
I think your statistic they can have, I'm pretty sure. Yeah.
Peter, isn't the limiting case here are metric graphs and not discrete graphs?
So
When you
it
shrink,
depends which part of the spectrum you're looking at, but if you're looking near a quarter, that's just work of higher than magnitude. Not metric.
not metric graphs, but this is, the question of small eigenvalue is really distinct from this. It's not random matrix theory, it's some other thing. Really small.
Looks like there may be a question on the chat. Is there
Yeah, there looks like a question. How do you operate this? I don't know. Someone wants to ask a question. I don't know.
Okay.
They just start speaking, will we hear them?
I'm going to regret this.
No, speak into that and say, please unmute and ask your question, see what happens. Just say
They
that.
can hear you.
There's
They
no
might be
mouse.
like-
Be nice to see if we can interact.
Then, so anyone has a question, right? Ask to unmute. Does anyone know how to operate a Mac?
Everyone, we like watching you try.
No, I don't know how to do this. Sorry. I just don't know how to.
Yeah, the
operate.
person can unmute themselves if they want, so.
Yeah. Yes. Yeah. Can I hear a question?
Yeah. So, yeah, I've been unmuted. Yeah, good. So my question is, are you aware of the correspondence that physics have unearthed between what you are saying with JT gravity and random matrix theory? I mean, what you just said has been done precisely, exactly in physics. I mean, in the correspondence between random matrix theory and JT gravity, because JT gravity deals with hyperbolic surfaces of higher genera, precisely. And there's a correspondence between such surfaces and random matrix theory, as you are pointing out. But I don't know whether it corresponds to GOE or GUE, because the random matrix theory there doesn't correspond to GOE or GUE. I just wanted to.
So I don't know this literature. I know a lot of the string theory literature where they were doing studying black hole entropy. They were looking at another statistic called the out of time order correlation theory, which also has influence of random matrix theory, but what they were doing was not averaging out all surfaces. The gravity theory, I don't know. The literature, I don't know that. I'll be happy if you can send me some pointers.
No, these hyperbolic surfaces of higher genera are precisely the surfaces which are the solutions of JT gravity in a certain sense. So what they do is they consider the path integrals corresponding to these actions which give rise to those solutions, and then they try to map the two partition functions on the two sides, the gravity partition function for JT gravity and that corresponding to the random matrix theory, and they find a complete equivalence.
Yeah, I'd be happy to see if you send me some of these references.
Okay.
There might be a way to use, I don't know if they know Mirzakhani's theory, for instance. Spectral. It'd be interesting to actually try to apply any of these ideas there, or to see if they have some other. So recently, there are a lot of people who've been following this conformal bootstrap thing. There's good ideas to study this one quarter problem. Another question here. Yeah. How you doing?
Yeah, can you consider the same problem? Did you investigate it if you mark points on, if you take MGN, if you mark points on the moduli space on the curves?
You should look at this. Definitely. So Mirzakhani's theory will work though for sure.
Yeah, that's what.
There is a trace formula in that setting, which I looked at very briefly. I haven't tried. The answer is I haven't tried, but it is feasible to try and look at it. I don't know in advance whether it
Or if you put levels, or if you consider the curve with the level structure.
That's a discrete thing. This I don't know if one can do it.
Any other questions? Yeah.
So if you're the 2 mod x, is the first term in the Taylor series of the form factor.
Exactly. The simplest part of
yeah. So for the GOE, there are higher terms, which would appear if you didn't have this limit that you take with if the size of L was smaller. So can you do you know how to get those higher terms?
No, I do not. One of the advantages of using this linear statistic is that you don't need to see this. You don't need to see this. But it would be very nice to be able to do this because of this large unit length and prevented to do it. I do get in some else was asking if there are remainder term. After taking the large units limit, there is a remainder term which depends on L, but it's just to get a balance. It's not asymptotic. So it's fortunate, unfortunately. It's by design, but for listening, this is GOE is simple. If I was doing something like pair correlation in my greens, then I would be in trouble because GOE is some complicated. That's why GOE is not lower.
Well, let's thanks again. We can continue.